Hello, in this video I'm going to show you in detail how to count time and space units of a given algorithm. But before that, let me summarize what we have been studying so far. So in the first video, I told you that algorithm analysis is related to determining the computational requirements of an algorithm, and in particular in this course, we will focus on time and space. And time and space can be determined empirically or theoretically, and in this course we will go for the theoretical analysis. But to do a theoretical analysis, we have to agree on the model of the machine where our algorithms will run. And this is the random access machine model that has several assumptions and on how things are going to be executed. So when we are going to calculate time, we have to remember that the execution of instructions is sequential, that each simple operation takes one time unit. Simple operations are numerical operations and control operations. Loops and functions are not simple operations. You have to go inside them and see how many simple operations they are made of. Memory accesses take one time unit, and every single variable takes one space unit. And with that assumptions, we can analyze any algorithm. So this is the algorithm we are going to analyze in this video. It's an algorithm that takes as input argument a b-dimensional array and sums the elements in the diagonal. So if this was the b-dimensional array, the matrix, the result of running this algorithm will be 39. These are the elements in the diagonal. So 4 plus 10, 14, plus 14, 28, plus 11, 39. Okay, so let's go on analyzing this algorithm. So the first operation is storing a 0 in a memory position. So it's just a simple operation, a memory access. It takes one time unit and it's executed only once. So we will put here the number of time units and how many times you have to execute this instruction. Then this is another instruction. We have one memory access here and one function call here. Each of them take one time unit, so we have two. It's executed only one time, but because we have a function call here, we have to check what happens inside that function. So that's something we are going to do next. This is a really an abstraction of the function that calculates the length of the array. When you have a diagonal, you are assuming that you have a square matrix that is same number of rows, same number of columns. So doing that, we are going to store in L the length of the matrix, understood as the number of rows. And we will go to the, this is row and this is column. So we will be looking just at column 0 and we will get down to sum up the number of columns. So this is a simple operation. 0 is stored in a memory position. It takes one time unit and executed one. While we already saw that the while has, in this case, we have one memory access, two memory access for L for A, and we have one numerical operation. So we have 3 times unit. But this while is going to be, not the while, the condition is going to be checked n plus 1 times, where n is the number of rows in the array. So this is going to be 3 time units because of 2 memory access, LA, and 1 numerical operation. And it's going to be executed n plus 1 times. Now, inside the while, we have this operation. We have 1 memory read to get the number of L, 1 numerical operation, and then we are going to store everything in the same position. So we have 2 memory accesses, 1 numerical operation. This is 3 units, and this is executed n times. And then, lastly, we have 1 memory access for L, 1 time unit for return, and this is executed just once. So if we sum up this, we have 1 plus 3n plus 1 plus 3n plus 2, and that's 6n plus 6. So this is how many time units this function will take. So we go back here and to the original two time units we had to sum up how many time units the function takes, and this is what we have here. Now we go for the for. Oh, remember, loops are not simple operations, so we have to analyze them. So let's analyze the for loop. If you remember, a for loop is an abbreviated way of writing a while loop, and this is read like that. Start with the control variable I. In this case, I is set to 0, and then while I is lower than or equal to n, increase I in 1 unit. So we can write the for loop as that, and then we can count the operations. So this is a simple operation, one time unit executed once. This is operation, the condition has two memory accesses, I and n, and one numerical operation, and this is executed according to our context here, n plus 2 times. And this operation, again, we have two memory accesses plus one numerical operation, and this is executed n plus 1 times. So our for loop, just writing this, means that we are taking all these units of time to execute, and this is 10 plus 6n, where n is the upper limit in the for. So if we go back to our algorithm, we will have 10n plus 6 here. N, remember, all the time remember, n is the number of rows in our matrix. And then inside the for loop, we have this instruction. This instruction has 1, 2, 3 memory readings and 1 memory writing. So we have 4 memory accesses plus 1 numerical operation. So this operation takes 5 time units. And because it's inside the for loop, it's executed n plus 1 times. And finally, we have the return. We have 1 memory access, 1 return. This is 2 time units, and this is executed just once. And finally, we can say that this algorithm under the RAM model takes 21 multiplied by n. N is the number of rows of the matrix plus 22. So this is an algorithm whose time requirements grow linearly with the size of the matrix. And that's something we are going to be back to in a minute. So this is the way where we have calculated the requirement of time. Notice that we are using a function here. The time required by this algorithm is a function of n, where n is the number of rows of the array, and this is the function. Quickly, let's go for the space units, which are much easier to calculate. We just go here. We are creating one variable, so that's one space unit. We are creating another variable here, n. A is given to our algorithm. It's an input parameter, so we don't count it as part of the algorithm. And instead, we have to create n here, so we count n. Then we have I. We are not creating any more variables here. And if we go to length, we can see that while length is being executed, it requires only one space unit, L. So when we are at this point of the algorithm, we require 1, 2, plus this, 3. As soon as length finishes, we go to here and we don't require L anymore. So all the time, the algorithm is requiring a maximum of 3 space units. So this is how you count the number of time and space units in an algorithm. And I have to tell you that estimating the time in this way, it's really tedious. We don't really like it. So this is the bad news. The good news is we can avoid most of the tedious part, and I'm going to show you how and why in the next video.